and today these states are at less than 10%. So given that, it's going to be a very, very steep curve that these states will have to climb if they want to meet those RPO targets and get into, meet those targets as expected by the state regulators and the national government. So this needs thinking along a very different dimension or very differently from conventional thinking that has dominated our energy planning. It needs to, you need much more out of the box thinking for that. In addition to that, we also have other issues that could complicate this matters further, especially for a states that perhaps host the significant part of the domestic steel market in particular, but also steel industry in particular, but also other heavy industries. The upcoming CBAM that Europe has proposed, the carbon border adjustment mechanism that Europe has proposed from 2026, as I said, I'm not an expert on the eastern states. I don't know how much of the industry here is export dependent, but whatever export dependence is there could get affected again significantly, and the CBAM will be a major factor. And we also had a little bit of discussion yesterday on the domestic carbon market. So these are additional issues that are going to complicate the energy planning for these states and need to be considered. So I will very briefly touch upon three issues that we have some thoughts to share about in the context of energy planning. One is how should the state be looking at planning for the future? How should the state be thinking about optimally utilizing the coal capacity that they have? And the future of state-owned generating companies in these three states. We think that these are three important issues that need to be talked about. I'll very briefly touch upon them and end my discussion. So the first thing about the planning for the future, as I said, is that the sector is changing very dynamically. The technologies, economies, as well as other factors are changing very dynamically. And going forward, one needs much more robust, analytically sound planning as compared to what one might call very seat of the pants, thumb rule based planning that has dominated the sector for the last many decades. We think that doing that, the risks involved in that are much, much greater. And to some extent, this is what has been indicated by the central government, and CEA has recently produced resource adequacy guidelines where they want much more analytically richer basis for planning. And one of the things that is highly underestimated in this process is the whole question of estimating demand itself. Traditionally, demand again has been projected forward largely based on past trends, assuming some perhaps at best GDP elasticity kind of approaches. We believe that this is not going to be a valid or a sufficient going forward, especially as we see newer uses of electricity itself, as electrification of more appliances, more end users such as transport and industry take place. Your entire demand patterns and demand sources will change. There is a big push to move agriculture to the daytime. So there are proposals to introduce time of day tariffs. There are going to be smart appliances which are going to come in. And there are going to be things like open access and captive, which also we talked about briefly yesterday. So all these are going to change demand patterns. In addition to that, you add growing affluence, increasing temperature, which means people will use more cooling appliances. And technologies are changing on the supply side also. So given all these things, business as usual approaches to estimating demand and planning based on that, we think will not be sufficient, and we really need to do much better than what we've been doing. Again, these are just a couple of examples of our work where we've tried to do some of these things. And based on this more robust demand estimation, we also need more rigorous, what is called as integrated resource planning, which is nimble and scenario driven, especially because I think of two reasons. One is the sector itself is changing so fast, technologies are changing fast, economies are changing fast, storage hopefully will improve fast on the one hand, and on the other hand, some of the technologies, unlike earlier, let's say coal-based plants and hydro-based plants, required long gestation periods, had much greater kind of windows of planning that you needed. Unlike that, the newer technologies that we have fortunately have shorter windows of planning, and therefore you can adapt faster to changing technology also. So given all these things, one really needs to do much more nimble scenario driven planning to account for a changing future, and it's not that you do planning once in 10 years and then you hope that things will work. We think now these scenarios need to be revisited every 2 years, and you kind of come up and change your plans as required because things are changing rapidly. The second topic that I want to briefly touch upon is optimal utilization of coal-based capacity. And fundamentally, the reason for this is that, and again, all these things that I'm saying, because one thing that often gets conflated is when I'm talking about, let's say, improved planning or optimal utilization of coal capacity or increasing renewables and meeting RPO targets, it's not that we're talking of any change overnight. All these changes are going to take time. Coal-based capacity is going to be around, we know, for at least a couple of decades. But these are extremely complex transitions, and that's why it's important, we feel, that we should start discussing them and start at least taking baby steps towards managing this changing world, so that as we go forward, we are better prepared to see the larger changes that will come, let's say 5 years down the line, 10 years down the line. We don't know what is going to be the case, but we should be prepared for it. And that's why it's important to start thinking about these things and saying that, oh, coal is going to be there for 20 years, so I don't have to think about anything for now. I don't think that is the case. And one of the fundamental reasons for that is, as we are saying, a change that's already underway in the Indian system. While coal still does supply 70% of our electricity, in the daytime we are already seeing its share dropping to significantly lower shares. And the reason for that is that from the firm baseload source that it has been, and it will be for some time, as I said, this is not an overnight change that's going to happen. But going forward, we are increasingly going to see its role change to a swing generator that is going to meet demand when other sources are not able to meet the demand. So that's a very fundamental change in the role of coal within the Indian electricity system, which means that all the other systems that we have around coal-based generation need to adapt accordingly. Today, the entire contract structure, the regulations, the policies, everything is built around this assumption of coal being a firm baseload supplier. This, we believe, needs to gradually change because its role is changing. It is not going to be fit for purpose. The current systems, regulations, contracts, planning mechanisms that we have, even financing mechanisms, if I may say so, are not likely to hold true for new capacity that are going to come forward because they're going to operate in a different world. So you need to think about how you're going to look at each of these things, and particularly so because, as we have seen in the earlier slides, a significant amount of capacity will even exist up to 2050. Any capacity that's already 2015 post capacity will exist till 2050. Anything that comes up now will exist till 2060. So by that time, you're definitely, one hopes that coal is not going to supply even 40-50% of our electricity. It will be much less than that. So how do you deal with that in those cases? What kind of contract structures and regulations and operational mechanisms will develop things? And again, we have a proposal in one of our reports as a discourse starter for that. The last thing that I want to talk about, which is unfortunately not something that I believe many states are talking about, is all the states, including the 3 eastern states, have their own state-based generating companies. And they are all very traditional coal-based. As I think colleagues from NTPC said yesterday, they are already, NTPC is ahead of the curve. They are thinking about the future. They are thinking about what new technologies they are going to go to. But what are the state-based generating companies doing? As far as I know, not many states are thinking actively about this issue at all. All the capacity of all the 3 states that we looked at, the entire capacity they own is coal-based. And one hopes and assumes that not much new coal-based capacity is going to come up under those companies. In which case, what are those companies going to be doing 10 years from now? Maybe for 5 years, yes, things will go on fine. They'll still be having a significant role to play. But we are not going to start thinking about what these companies are going to be doing 10 years, 15 years from now, slowly. Because all these things, you need to think about what kind of skills you're going to need, what kind of staff you're going to need, what kind of business plan you're going to need. You can't continue to live under a Section 62 cost plus regime where you keep putting in some money and the regulator will keep allowing you pass through of all the costs. So how are you going to adapt to a more competitive world where there are going to be newer technologies, whether it is storage, whether it is renewables which are going to come and compete? So how are these companies going to find a future for themselves? This is something that we believe states need to start thinking about because these are public sector utilities that definitely play a important role in the electricity system. But if we don't think about their future, they will unfortunately get more and more marginalized as we go forward. And one hopes that that's not what we want from these utilities. So these are some of the issues I wanted to highlight. Just to conclude, basically, I think there's really nothing new on this slide. It's just that energy transition is a complex multidimensional issue, particularly so in the eastern states, which are heavily dependent on coal-based generation and minerals in general for both their revenues as well as for their energy. And therefore, one needs to really think out of the box, think very differently for transitioning to a renewables rich system. And you cannot be wearing the old thinking hats that have led you to the state so far. You really need to think differently if you want to be prepared for the future. So that's where I'll stop, and happy to take any questions.
I think we'll keep the discussions to the end. We will first listen to all the speakers and then have the discussion. So, may I now invite, okay, since we are discussing the policy things, can I call Ma'am Sadamini Sethi, Additional Secretary, Steel and Mines Department, to share her inputs on the state government's initiatives.
Carbon factor and all the energy, all these are technical issues that are not related to our session. We are only implementing the policies and the decision taken by the government. That's why we are least concerned about the all environmental issues and all factors we are discussing. It is also learning for me that I have meet all the prominent and speakers, those who are tell about all these things. But as relates to our state, no doubt the Steel and Mines Department, we are having total 52 of steel plants in our states, and out of that seven plants are mega plant that are producing more millions of production. And as relates to mines, there are 640 major minerals are in our states. Out of that, 148 is working and 127 is non-working. Other rest are very year back and it has not yet surveyed. As regards the pollution or the environmental concerns, all of we know that the mining operations are started by the, no doubt we are conducting auctions and operations started after they are getting the FC and EC, and we are giving 3 years at least time for getting then we are signing mining development plan agreement with that party concerned. No doubt the steel industry or the mining sector are more held responsible for the development of emission of the CO2 and responsible around 240 million tons per annum. But we are in our department, we are made a strategy that is one of the energy vision document in consultation of PwC in the year 23-24 for sustainable development of the steel and mines and the emission of the carbon emission purpose. And another, our forest department also take initiative for conducting or creating an action plan, energy action plan that collaborating the 10 to 12 departments. Recently on around September we have also make a study and a great discussion, and we are also giving the inputs. As because Steel and Mines Department is directly not related to the preventive measures. All other departments are working on this and we are just supporting to them. Now I request Forest Department Surin to what action plan, energy action plan we have prepared for Odisha, better he can tell. In this, I am thankful to all of the participants, and no doubt this is my statement that this should be more research based to reduce. No doubt the carbon factor is a future hindrance for all of us. It should be make more viable and more friendly to cross all the environmental or climatic changes what we are now facing. It will, perhaps it will be more than double we expect that in 2030. Therefore, we should be our since today that all states and all research based work and unit based it should be done. What would be the cost effective, both seeing or giving importance to the economic and the social factor. Then if it will be planned, then we will seek a platform from our department to implement it or to make it as a rule or act for preventing all these hindrances in future. Okay. Now I am switch over to Mr. Surin to present.
Scientist in State Climate Change Cell that is administered by the Forest Environment Climate Change Department, Government of Odisha. So Forest Environment Climate Change Department is the nodal department in the state to carry out the all climate change related activities in association with 11 major stakeholder departments, which are like Agriculture, Farmers and Environment Department, Energy Department, that is from Revenue Disaster Management perspective of view, then Fisheries and ARD Department, and Industries Department, Steel and Mines, Commerce, Transport, Water Resources Department, Housing and Urban Development Department. So these are the major stakeholder departments for formulation of the State Action Plan on Climate Change in line with the National Action Plan on Climate Change. And recently the Odisha has got the approval for the State Action Plan on Climate Change 21 to 30, that is based on the NDC guidelines, Paris Agreement 2015 and the Sustainable Development Goal, and Odisha is the first state to get approval for this State Action Plan on Climate Change. So basically our responsibility is to act like a single window with the Ministry of Environment, Forest and Climate Change regarding the climate change related activities. And yes, mining sector is one of our sector in the State Action Plan on Climate Change. So basically, what are the directions that have been placed in this action plan in the climate change in relation to this mining sector? Just give a brief view, not taking more than the busy more time. The state government of Odisha aims at achieving the optimal utilization of state's mineral resources for its industrial growth and socio-economic development through scientific exploration, sustainable mining practices, and geoscientific research. So what are the impact of climate change if we are focusing? According to IPCC's 5th assessment report and subsequent observations of the climate change network in the country, so mining sector will be affected by this climate change impact. So the high level of precipitation will increase the rainwater infiltration on spoil piles, resulting in aquifer level contamination in coal-bearing areas. The water quality of nearby streams may be affected for that reason. Then concentrated rainfall will also increase the risk of mining operations and damage the outbound transport infrastructure. Then changes in the frequency and intensity of storm events could affect mining operations, example tailing dams, sediments, erosion control. So however, these impacts must be addressed as part of the mine's water management plan in a changing climate scenario. The atmospheric pollutants from primary aluminum production also produce acid rain when they mix with the water vapor. So this type of industries they are taking serious concerns, and they are taking the actions in this regard. So now the excessive heat that is likely to prevail in the summer months in the northern and western parts of the state would contribute to workers' heat strokes, cause more mining accidents and shorter working hours and lower productivity. So these are some of the directions, dimensions that has been addressed in the state action plan on climate change, how the state government is taking policy decisions through this steel and mines department, energy department, all of the departments. These are working in close relation to the climate change. But that's just it. Thanks.
Mr. Sujit, for providing us the idea as to what the environment department is doing. And I think NCAER team actually has also covered this climate action plan of the state in the report. And okay, so I think we'll now move to Dr. Santosh Kumar Sahu, who will listen to him about the carbon productivity of the industry. And in fact, okay, he can talk about their center also. They have a sustainability center and their work briefly can tell, and then coming to the work.
Good morning, everyone. Thank you, Professor Das, for this opportunity to present the work in a forum which means a lot, being a Odia, coming back to Odisha to present something interesting. So I am Santosh from IIT Madras. I am an economist by training. I teach in the Department of Humanities Social Sciences. I teach in the Department of Humanities and Social Sciences. At IIT Madras, we have first we have a center where we are working on energy and climate change related issues called Energy Consortium, which basically have scientists, engineers and policymakers all together in one platform, along with industries, because industries' problems are only discussed within industries in terms of their commitment, their policy requirement, etc., unless we need CSR fund. Right? So the industries have different ways of looking at it. So we collaboratively work on developing tools and technology for them in the center. Professor Rajneesh, who has to unfortunately go because of some personal commitment, couldn't present the technology that we have done a lot of IT on that and already installed in Chennai in one of the industries about carbon capture technology that yesterday we were talking about. Now, the recent development that IIT Madras has done is a School of Sustainability, which is larger in terms of educating not only the students but also the professionals who need a training, either CXO or CEOs or even government officials, is one step ahead after we realize the need for a School of Sustainability, which also have people across the board a complete interdisciplinary approach to understand sustainability, looking at each sustainability goal. Now this work that I am presenting has multiple layers. One is it's pure academic. As per my own academic research is concerned, I have been working in the areas of energy economics, particularly industrial energy economics, for around 10 years now after my PhD. And partly we are also concerned about the industrial, when we interact with industry, we learn more than the data that is given in the CMI Province database or ASI database when it comes to policy making. Now one major issue that is discussed from yesterday and many other such forums are, we all are concerned about climate events, we all are concerned about emissions. We are a little bit more careful about CO2, particularly because of the scientific problem that it has. And majority goes in the GHG emissions criteria. So therefore controlling CO2 emission is one of the ideas that everybody is concerned about. But then the question is how to price it, can we price it? And if we price it, then is it going to reduce the emissions or is it going to be financial outlay only in terms of technology transfer? So going back to the IPCC-led Clean Development Mechanism in 2012-14, India started that process but couldn't continue on that because there is no standard protocol or framework which enables each country to need a kind of pricing. So just a number, if we know about it, it ranges anything between $3 to around $181 for tons of carbon. So $3 is basically the global average, and 180 is the amount that comes a preferable scenario to have technology intervention and change the technology so that emissions should be low. But the average comes around $50 that people talk about. But the trade-off is there that who is going to gain this 180 or $3?
Is this the social cost of carbon?
Yes. So I'm going to also present that social cost of carbon. So there is also a big debate going on how much the farmers in Africa are getting. So they get around $3, and the industries get around $180. So there is another different way of looking at it, whether there is an equitable distribution of that. But this work is not related to those aspects because we have started to understand the Indian industries by layering into different questions. Question number one, which are the industries that can adapt this change, and whether it will impact on the productivity, because economics of industries are largely dependent on the productivity gain and profit maximization. Now that is the first motive. So unless profit maximization and productivity gains happens, no policy will be accepted by the industries unless it is a directive policy or unless it's a compulsory policy. So voluntary policy doesn't happen. Now if you go back to the IPCC framework and COP meetings and etc., that is basically a voluntary activity, not a mandatory activity as of now. So therefore there is again a trade-off between how industry react to that, which industry react to that, and what happens in India. So I'm going to speak about how we have computed this, and for the benefit of all of us, I've skipped the mathematic part of it, and I'm going to present the results so that we know which industries can be targeted in which capabilities. So obviously yesterday all of us discussed about the movement. In fact yesterday it was a very interesting presentation by Terry where the history of Kyoto Protocol and the engagements were discussed. So I won't repeat those elements, but what is interesting for me is, as an Indian economy, am I going to lose or am I going to gain out of this entire engagement? And whether my industries here in India are going to be beneficial or they are at the cost of production or value chain, or maybe international trade which will affect them, so that we will have an adverse impact on the economic growth. That is more concerning than what happens in the high income countries, right? For example, per capita energy consumption in US is way above than what we consume in India. So catching up with them is one condition, and not catching and paying the price of not catching is another condition that basically comes into argument as a policy, the policy work that we do. So therefore the pollution pay principle is what largely being accepted, but again it depends on the statistics that we talk about. That means, are you talking about the growth rate of pollution, or are you talking about the aggregate pollution? So growth rate, yes, India is growing and therefore infrastructure is growing and therefore pollutant has to come. But then if I compare that with, let's say, the economy of US, then probably I'm not doing a justice with the emerging economy like us, where majority of people do not have car. That's exactly what yesterday one of our speakers was talking about, that people do not have car, people will have car. Now unless we have car, our GDP doesn't go up, money doesn't circulate and income doesn't go up. So in this context, if you look at the carbon profile, all of us here know about it, but some interesting recent fact of 2023 is agriculture also equally emits around 21%, which is not a smaller amount, and manufacturing is 17% according to the recent IMF report that has come up. And power sector is largest emitter around 37%, which is true because it's a largely thermal based power sector that we have in India as of now. So for convenience purpose, what happens is sometimes we mix between the power sector and the manufacturing sector. Now one of the reason is manufacturing sector also has captive power plant. They generate their own power plant, their own requirement, because they don't get adequate energy in certain geographical locations in India, or even they need more energy at a lesser price. So if we just remove the power sector, then manufacturing is 17% and transportation sector is 9%. Now the problem is transportation sector is not an independent sector. It's also a sector that basically helps all other sectors. So therefore the emission profiling classification becomes really a subset of each other. They are not independent, identical to each other, but they are subset to each other. But then we have a larger goal in India. Recent policies of Make in India and other activities, even Digital India is one of the initiatives that is going on, and where service sector has also started emitting faster. So I mean, one interesting thing is when I fly, I see that Chennai Airport is working on decarbonizing in the aviation sector. So that means aviation sector is also equally responsible for emitting the emissions. So can we now think about pricing emissions from the Indian perspective so that the price per unit of carbon emitted is agreeable by both policymakers and industries, which will maximize the welfare of the people at the end. So there are many questions that comes in this argument which require a lot of investigation by many researchers across India. The first question is, are we ready to price carbon? Because the question that we are dealing is, there are two fronts we are working on. One, whether we price the material, that means whatever material you consume, we price it, that embedded in the carbon pricing. Second question is, let us not tax the material, we tax the output. Then if we tax the output, that is bad output generated externality in terms of emissions, then how to measure it, who will measure it, how to create an accountability framework on that, and do we have a institutional support of getting those kind of technology installed to figure out what is the emission that happens at each unit of industry that is located. Now, if you look at data for mostly people we in economics, we have aggregate data of emissions. We may have sub-aggregated data, but we do not have plant level data to work on these kind of emission activities. So either somebody has to do a survey, which requires a lot of money because survey is not free of cost, or we have to come up with some scientific approach where we cut it from the bottom-up approach. That is exactly what we have done. What we have done in this work is we have computed the emissions factors by using the recent IPCC framework, by assuming what are the energy mix that industry consumes and what will be the minimum level of emission in a standard protocol. So the limitations are the following. First, we are not able to estimate for electricity use because it's a double byproduct. That means somebody produces it at a particular location, that is being transported, T&D loss happens, and then you consume it. So it's difficult, it may lead into double counting. Second problem is, we assume that the technological frontier of each forms are similar because we are computing it from the energy use profile. We are not computing it from the technology profile. So example, one form may be very efficient, another form may be lesser efficient, but we still assume that all forms are homogeneous in terms of energy consumption, and therefore this is the minimum that they are going to emit. Now, if we can do that and go in terms of the, if we can calculate that, then what we can benefit from this work is basically we will reduce the emission gap framework that we actually emit and what we basically promise that we are reducing the emissions. Right? This will help us in creating a policy document for us where we know that yes, this is the amount we are emitting, this is what we have promised, and what is the gap. And of course, a differentiated policy will come from the manufacturing sector. Now, obviously, let's not discuss about it, why India is important. There are multiple reasons. One of the major reasons, what I feel is energy security is something which we are all concerned about as macroeconomists or microeconomists, but the burden of oil is very sensitive for India in terms of growth paradigm. So we have to think in terms of whether energy security can be one of the major thrust in computing the carbon emission and bringing in RE the way we are bringing it. So we have basically oligopoly market. One market led by coal or fossil fuels, the second market led by the renewable energy. So that we have two markets to function, and therefore what happens, our degree of insecurity in energy reduces. So for that purpose, what we have done, there are around 70 types of sources of energy being consumed by Indian industries, starting from derivatives of coal, derivatives of petroleum products, ending to husk or any kind of traditional fuel that is used. So the best examples are brick industry are using in the lower of the ladder, and steel industries are using in the up in the ladder in terms of the heat or energy requirement. So what we did was we took the industry data and at the level of form, we integrated between the annual survey of industry data and CMI progress data, which is basically the two biggest database for the industries. And this data representation are only for data that is derived from these two sources. So what we did, we took the 70 type of energy being consumed, converted into physical unit, converted further in terms of the emission coefficient, computed emission coefficient for each of the forms in the data set, and then try to look at two behavior. One is how much you emit, what is the price. That is the only context that we are talking right now in this particular presentation. So if we look at the emission is, the red line is the emission growth and the blue line is basically the emission in physical terms. So aggregate emission is growing, but the growth rate is reducing. I mean, that is exactly what people want, right? I mean, the idea is probably not to reduce the aggregate one, but let us reduce from the growth pattern. But when we put the price on that, what is the price the firms are paying today in consuming those goods and those materials in terms of either embedded technology import from coal or outside India or buying from the Indian market, then energy prices and its growth are converging. Right? So basically the firms are doing a trade-off between the price. So they are not doing the trade-off between emission, what happens, how much emission is going forward. So therefore we thought, let us have a carbon price mechanism, come up with some equation which will help us in quantifying that. We have used couple of parameters where, let's not discuss, if you want I can discuss more on this. So basically we calculate emission weighted carbon price. So the condition here is, you pay for the energy which doesn't have a carbon price. Now I compute energy with carbon price. So you can see these industries where the differences are negative. For example, the nominal energy price that they pay and emission weighted carbon price. That means I just take one example of textile. Textile pays around 69 or 70 rupees per unit of consumption, and whereas the emission weighted carbon price is much lesser than what they have. And one of the reason is, I can also tell you, we have another center at IIT Madras which is taking primary data of textile industry alone. So one of the major problem is they have a very poor energy management system because it's a low-tech industry. So leakages are more, wiring are not done properly, not so much of technology is required, but something like Six Sigma is required where you train them how to use energy. So the loss factor is higher. So they pay more, but if you convert their output and energy use, they basically are the industries which have lesser carbon weight factors. So we call this as low emission weighted carbon price, low social cost of carbon, and their energy dependent sectors. So we need a technology development in this sector so that the loss of energy or the loss of useful energy would be converted into more useful energy. And therefore what we propose, we need a energy price reforms in this sector. So right now if you go for a policy, we may not need carbon policy for them, but we need a price reform in the energy policy. Similarly, we have other industries where we have the differences are quite high. And interesting thing, you can look at the 26th NIC classification at 2 digit, which is computer, electronic and optical product. Now this industry never talked about, we never talk about this industry, that this industry may be carbon intensive or social cost of carbon is high. But we figure out that even this industry, which is a service or a manufacturing led computer aided IT/ITS industry, this has a high emission weighted carbon price. So this industry, we need carbon policies. So we cannot have only energy policies for them. So we should have differentiated policy based on the carbon profile that they come up with. So these few industries, from food industries to chemical and chemical products, that includes the pharmaceuticals here, have a high emission weighted carbon price and high focus sector. But interestingly, there are also some industries which are, okay, that's the next one. So the question therefore is, if this path continues, what will happen in the 2021? We just projected a trend line in a linear fashion to look at what will happen between emission per tons of kgs that we have, thousands kgs, and the growth rate. So we are reducing, but we need more time to reduce on that. But then the question comes, if we input a policy and these industries will be sensitive enough not to grow, then what happens is we have a disequilibrium in the domestic market. To address that, what we did, we basically tried to put a price reform on the carbon front. So this price reform, the first effect of price, the average price, comes from the average of these emission weighted carbon prices, which matches with the $180 which was being computed in the international scenario. But if I allow a little liberal policy, and what do? I will reduce it for $30 per ton of carbon in India. Let us go below the $50 and put it $30 is the beginning, what is going to happen. In that scenario, what happens? The emissions reduction will come down from 50% to existing 50% target to 40%. So that means 10% trade-off comes when you change the average price to the minimum price of 30. We can do with other numbers as well, 10, 20, 15, whatever number comes, we can estimate in a different scenario in that case. So therefore, at the beginning, the hypothesis or the suggestion is, let us start with the lower price segment where the industry are ready to enter, and then increase the price gradually, because technology development will happen in a long run. But then the question is, why should an industry will agree? Because they would like to link it with carbon productivity. They will look at into the productivity part. So if we bring the technology part, so we created something called carbon productivity index. Now carbon productivity index is in presence of the carbon pricing mechanism, how the productivity change will happen. A value which is greater than 1, in this case you can look at the pharmaceutical is 1.09, which means if when the pharma companies are emitting more, at the same time they are able to produce more than the proportionate amount of emission that they do. That means if they emit 1 unit of carbon, they are able to produce 1.909 unit of output. So these industries are high carbon productive industry. That means if you include reform, they are not going to have a problem in terms of output change. They will have a positive output change. But at the same time, there are industries which will suffer. That means if 1 unit of carbon emission happens additional, then the output falls down. That is, which is 0.89, 0.86 and all the numbers that you can see in the extreme left hand side of the table. So there are industries which will suffer in terms of losing productivity. There are industries which are going to gain out of it. So the industry which will gain are these pharma, rubber, plastic and textile. Industry which are going to be affected are these coke, computer, electrical equipment, food product, motor vehicles, pulp and paper. So we need different reforms for different industries. We cannot have a homogeneous pattern if we look at in terms of the carbon productivity. But interestingly, there are some industries there is no change is being reported. That means 1 unit of additional carbon is not going to change their output. So they are the stagnant industries. So you need massive reforms in terms of scaling of these industries, because for example basic metal is a resource dependent industry. So it becomes a challenge for the government to increase the scalability at a short run. So these are the industries which are not affected in short run. The effect will come in the long run. So therefore, what kind of policy we can think about based on these two arguments of price, carbon and energy profile? First is tax policy, which we are talking about either in terms of carbon tax or carbon pricing, and we have to choose between them, and also we have to discuss about whether we talk about the footprint analysis or we are talking about the emission profiling itself. And we have to have a sectoral level social cost of carbon and regional level, because as we were discussing yesterday, Odisha supports majority of these states in terms of natural resources, but on the burden of high emitting states. So the reallocation of fund from federal approach has to be taken care of, so that states like Odisha, which are resource dependent, or Jharkhand for example, will also get the benefit of allowing to utilize the resources that we have to other states and other countries as well. Then of course heterogeneous policy at critical in terms of the nature of the industry has to be done, because we cannot have a single window policy for all the sectors without understanding the carbon profile and the technological changes. And of course technology will help. For example, CCUS is one of the technology developed and deployed from IIT Madras, and many other IITs and institutions are working on it. So we have to increase high amount of fund for those kind of research, which will lead into a positive output for installation in those factories. So we can start installing in the factories rather than installing as a welfare measure across the state, because the industries are emitting. They know how to convert into the price mechanism, so they can accept it in terms of technology adoption. Now, given CSR has become mandatory now, so industries can also use their CSR fund to deploy this kind of technology, to give institutions of importance and institutions of national levels to continue to do this kind of analysis, where they can basically club in terms of a industry academia project, which will not only give intellectual property rights but also come up with a large scale of technology to utilize in the industries. And of course, the one important thing is increased fuel mix and energy substitution at farm level is important, because the 70 types of energy sources are pretty big in terms of number when we look at, which is a complete heterogeneous energy profile for Indian industries. Unless we minimize that and come up with solutions which type of fuels could be used by the manufacturing firms, and come up with a policy with energy accounting as one of the major elements, it is very difficult to regulate this sector. And given that our analysis does not have MSMEs, right? So we are not increasing even the number of fuel type. If you include MSMEs, small sectors, then obviously the number of energy types will go on more than 70 types. Right? So these are the observations that we are working on it, and right now the next step that we are doing it, we are going to have some kind of a, we'll have some kind of an NCAER analysis of these technologies that is developed at IIT Madras and otherwise, and because that would give a clear clarity of calculating the carbon footprint, because it is not one time, but what is the life cycle of a particular technology, how it is being deployed, used, and what is the probable emission that might come in. So thank you very much for the opportunity. Questions I am ready to take either now or after the yeah.
Okay, I'm sure there are a lot of questions for it. Don't worry. Okay.
Thank you everyone, and thank you Amarendra for inviting me. Just a disclaimer that I'm a device physics guy. I'm trained physicist and I make devices and technology, and I might not be a complete fit to the economic jargons which have been communicated in this panel and in this discussion. So nevertheless, let me try and contribute what we can do. So I have a device physics lab where we work on different types of technologies based on solar cells, and we are adequately and plentifully funded by the Department of Atomic Energy and through NISER. To a large extent, yeah, that's correct. Yeah, that's exactly the reason why. I mean, generous funding compared to other funding agencies. That's appropriate word. Yeah, correct. Thank you. So mainly, yeah, I just want to impress upon him that yeah, we expect more funding. Yeah. So coming back to the context, so we work on solar technology. So we try to develop a large number of technology. So basically, this is the energy map of India, where we see a diverse technologies which are used for generating energy, which includes obviously coal, which has been discussed widely. Then we have oil, petroleum, natural gas, nuclear forms a substantial part, and other sources. Then we go back to renewable energies, which is solar, wind energy, biomass, and other possible sources of energy. But one of the important things is solar can be a big source of energy for India, and particularly for the eastern part of India. Although we have, if you see the energy distribution, I don't know, this part of the graph might not be clear. This has been taken from collaborative research by Ministry of New and Renewable Energy as well as NREL from USA. So what happens is the amount of energy, as we can see, the density of energy could be lower compared to the western part of India, but it's substantial to take care of large part of the energy demands of Odisha or in the eastern part. So this is a technology which we can't ignore if we want to go for a net carbon zero future in 2070. But there are certain issues which was also discussed earlier yesterday and maybe to some extent today. So one of the pertinent issue is about if you want to install solar panels, we need a requirement of large land areas which will be utilized for installation of solar panels or solar power. And then there are issues related to incorporation of these solar panels to the grid, and what are certain technological implications, what are the issues, like what are the limitations and how it's going to affect the power grid. And obviously we all are aware that it is difficult to store this energy, specifically since it's intermittent, and specifically when there is no solar light, how we're going to use and take care of the loading factor in the energy sector. This is highly weather dependent, so we have a cloudy day, the efficiency of the solar cell can fall down from 25% to around 10%, which in that case we will not be able to meet the demand and supply. And the final thing, which is not too much discussed, is actually solar panels have a lifetime of 25 years, for example. Then after 25 years, how we are going to dispose this e-waste. So that's a challenge which has not been addressed to a large extent. I will try to tell in this panel how we are going to help in contributing to solving some of the issues, but not all of them. First thing is about the large area which is required to install solar facilities. So one of the things which we could do is typically the solar panels which we use in our domestic consumption or in some industries or in aviation industry or different industries have a typical efficiencies of around 12 to 15%. That's what is commercially available. But at the same time, the research has gone to a large extent where we are able to get much like much smaller area solar cells where efficiencies can go up to 25%. At the same time, the prices are comparable or sometimes cheaper than silicon solar cells, which is what makes this technology could be a disruptive thing, which is not discussed abundantly, but there are possibilities which exist. For example, I don't know if my person is seeing, so there are certain technologies which I want to point out here. For example, there is a technology of perovskites which actually has gone from 11% in 2010 to around 24% currently, which is trying to get commercialized with a company in Oxford, which is Oxford PV. So these materials are relatively abundant in nature, so they are made up of normal typical salts, and they're much easy to process, so the cost of manufacturing also comes down. And one of the problems which India has faced in terms of semiconductor industry is that the cost of investment which government has to take care. So this can be taken care of by using these cheap and abundant materials which are much easy to process, and they can be done at a small scale industry level, and then which can have opportunities of demonstrating very large efficiency.
Are you using this method?
So yes, that's correct. So we are in the lab stage and we are collaborating with a couple of industries in India and abroad to try and see how we can complement the silicon industry. So what exactly we are trying to do in collaboration with one of the companies in UK, that's called the Oxford PV. So what we do is on top of silicon, which is typically 12 to 15%, this is basically a paint which we paint on top of the silicon solar cells, and then the efficiency goes up to around 25%. There is an issue with this. The silicon solar cells are stable for 25 years or 15 years, 25 years, depending on what grade of silicon it is. But these materials are relatively unstable, but since they are made up of paint and they are much cheaper, so they can be easily substituted regularly in intervals of 2 to 3 years to get back the efficiencies. Moreover, these can be easily painted into windows and other paints of the building, and they can be a source of indoor lighting, which can actually decrease the power load on the grid. This is one of the things which I want to point out, that if we are able to have different materials and disruptive technologies so that we are able to get large efficiencies in smaller land areas, then our problem of land consumption will decrease. Coming back to the next issue, so whenever we want to incorporate solar cells into the grid, we have a problem of voltage fluctuations, because obviously it's an intermittent power supply, and then we have short circuit conditions. There are issues because of weather conditions or because of external factors, the solar cells can get shorted, and this will actually create a loading factor in the grid. So this is a thing which needs to be tackled, but it can be tackled to a large extent if you have a proper energy storage. If you have a stable battery source and the battery has a larger time of retention of the voltage, then we could tackle this problem to a large extent. So there have been technologies like supercapacitors, which actually charge much faster than conventional batteries, and they also retain the charges or retain the charging for a longer time. This is something which people have been working through in the country as well as other leading universities abroad, where we are trying to develop technologies based on supercapacitors, which actually can charge faster and also retain the charges for a longer time, and possibly solve the problem of this grid incorporation of the solar cell technology. Oh, there is some problem with this. Okay, maybe I'm sorry for this. So what I want to finally point out, coming back to the problems maybe, so if the large area requirement, large land area requirement can be solved by using high efficient solar cells, the incorporation onto the grid can be solved by using batteries and supercapacitor, which could be new generation technologies, and obviously we can't resolve weather dependencies. But then there is a thing, when we have a cyclone in this eastern part of India, though we have power cuts for months together. But if you have a localized off-the-grid setup for each domestic user, which is what Prime Minister inaugurated recently, I think in Delhi. So if we have a localized grid for localized domestic consumption, solar panels for domestic consumption, if that is encouraged by the government with the collaboration with industry, so that could could solve the problem. Specifically, if you want to go to areas where the grids cannot reach. There are certain regions in Odisha and certain regions in India where the grid accessibility is limited and low. In those cases, if you have domestic solar panels provided for off the grid application for lighting for the lighting at the local levels, then possibly we can resolve this issue to a large extent, and we might not have power cuts or loading when we have cyclones disrupting the grid completely. The disposal of waste is a major problem. It needs to be thought about. It needs to have a policy set up, because this is effectively an e-waste which we are generating. So that is something which we have to think about for the future. And finally, I just want to point out that Odisha has great potential in terms of the energy received from sun. It turns out in the last slide we had these numbers which somehow were disrupted. So it's around 900 watts per meter square, which is a really huge number, which is comparable to what people receive in Uttar Pradesh. So it's a reasonable number, and if we are able to use solar panels in our wastelands and certain reservoirs, then possibly we can solve the energy problem of Odisha to a large extent. And thank you for the opportunity.
Okay, thank you so much. I just have a quick question. The minerals, are those minerals available in Odisha or India?
Yeah. So there is only so most of the materials are basically salts which are available in India. The only thing which is not available is indium tin oxide, which there are two countries which are the major producer, which is China and US. That is something which needs to be taken care of. But then most of the indium tin oxide which is used in display technology or mobile phones are generally recycled for using in solar panels recently. So that is something which can be done.
Thank you so much. I think you have really connected well to our what's our discussion.
Yeah, thank you.
So now I shall invite again another scientist colleague of mine, Dr. Vishnu Prasad Biswal. He is also coming up with very high impact factor publications. He is the celebrity in our campus now. Now Dr. Vishnu Prasad Biswal is working on green hydrogen related issues. So he will tell us about the issues related to the green hydrogen.
Yes. Thank you, Dr. Amarendra, for giving me this opportunity. Actually, I am also one odd man here because I am no way related to policies and all. So we are basically, I am chemist. I work in chemical science department. I am experimentalist, so we do experiments. So primarily my research is based on several aspects, but we try to address social problems like hydrogen production, hydrogen storage, and also hydrogen separation, which we use membrane technology to separate hydrogen from impurities, so that we get more pure hydrogen and we can utilize it to get maximum efficiency. That's what we do. We try to do a lot of synthetic work to get materials for hydrogen storage. That I will a little bit highlight what we do. We develop some catalyst that can split water, because water is composed of hydrogen and oxygen. Okay, so if we can find out a way which doesn't happen at room temperature, so if we can find out some catalyst, okay, and by using electricity and or photo like basically sunlight, we can split hydrogen and water, so that both are helpful for us. Oxygen is also useful and hydrogen is also useful. Yeah. So already there have been several discussions and very nice things, although I could not attend all the things. But there has been intense discussion on fossil fuels, how it is threat to us, and they are emitting greenhouse gases and global warming. So all these things are aware to everyone. So I'm not going to talk on that. This Paris Agreement also, how we can reduce the carbon level, so that we can decrease the temperature to some degrees, so that all the problems associated with this will be solved. Yeah. So hydrogen, why hydrogen? Hydrogen is basically a very interesting thing. If you see the hydrogen, it is just H2. So two atom of hydrogen is combined. Something like there is no carbon at all. So that is why it is called a very clean fuel. So if we use hydrogen, there is no possibility that you can generate carbon dioxide or something. So it's very clean, and it is non-toxic at the same time. It is non-emissive, high specific energy. If you compare the energy, it is around the values, whatever I will talk, it's not very updated, but it's very recent values. So kindly excuse me for that if there is some deviation. So 120 metric joule per kg versus 44.5 metric joule per kg for gasoline. So you can see the energy density, specific energy density is very high for hydrogen. So which can act as a very efficient fuel for the future. And if we see the hydrogen basically utilization, it is almost 33% of hydrogen is used in oil refineries. They use it for their purpose. The chemical production, 40% of hydrogen is used, and welding processes, food industries, and the rest of the things people are using. Now the trend has come to utilize hydrogen for two major purposes. One is transport sector, and the other one is to get electricity. How we can utilize hydrogen to get electricity? That is, the fuel cell is coming into picture. You input the hydrogen, and it will combine with oxygen. It will give you energy, and the byproduct is water, which is very, very good thing. Okay. Of course, you need catalyst, you need some energy to drive the process. Okay, so that is what the scenario is. Okay, coming to hydrogen production, if you see most of the hydrogens, whatever is being produced, are electrolysis process, and efficiency is around 70 to 80%. But you have to give electricity as input to split it. And we are trying to get, by substituting this electricity, we are trying to develop technologies for solar-based technology. Suppose your input energy will be the sunlight, and under sunlight, with using some catalyst, you can split them effectively. So, being said that, what will be the problem like incoming hydrogen? Whatever the hydrogen will come, you need storage mechanism. Unless, because hydrogen storage has been the biggest problem. Okay, so if in the okay, so fine. So to produce 1 kg of hydrogen and 8 kg of oxygen, you need kind of 9 liters of very pure water. That is also a very problem. You need very pure impurity largely decrease your efficiency. But nowadays China has come up with some technology. They are trying to use like saline water or sea water, so that plenty of sea water is there. You can utilize sea water and sunlight. Then to get some extra. Of course, the efficiency will be a little bit down because of the impurities and all. But that technology is coming up, so that you can largely reduce the cost of the hydrogen. Hydrogen is also categorized into green hydrogen, grey hydrogen, pink hydrogen, and all based on the sources. So whatever hydrogen we get using electrolysis and all, because at the cost of 0 carbon or something, that is considered as green hydrogen. So which is very important, pure hydrogen. Okay, so coming to hydrogen storage, if you take 1 kg of hydrogen gas capacity over, it will take 11 cubic meter space area. So okay, liquid hydrogen also, if you want to store, then you have to get this very low temperature, cryogenic conditions. Otherwise, you cannot store it. Gaseous hydrogen you cannot store it because it needs large volume containers, which is very big problem for us. And liquid hydrogen, if you want to do, you have to first convert this gaseous hydrogen into liquid hydrogen. So you have to put energy, high pressure, as well as the temperature has to be if I give you a value 250 degrees centigrade, minus 250 degrees centigrade. So it is very, very low. So that is also another problem. So what we do, and in order to store them, you need 700 bar pressure. This is 1 atmosphere, leads to 1 bar pressure. You can just see 700 bar pressure, like how much the pressure will be. So that is the problem of hydrogen technology. So what we do in our lab, we try to develop material like sponge materials. If I give an example, suppose you have a sponge and you put in water, what it will happen? It soaks. Okay, so our materials, they have very small pores, throughout, it is interconnected. So if I give you one example, suppose 1 gram of material you take and which we can hold on your palm, which would take space like one coin, like 1 rupees coin or something. That will have surface area of 7,000 meter square per gram of material, 7,000 meter square, which is equivalent to a mini football field. So you are kind of holding a football field on your palm. So that power that porous materials have. And in terms of another example, if I give you, suppose you are having one LPG cylinder of 17 kg or something. You want to use those porous material 1 kg of materials, then you can fill 4 times gas, more gas. So one cylinder would run you for the whole year. So like 3 months if we take like average consumption of 1 cylinder. So that is the new technology that is coming up. Recently also there was an quote, yeah please. So there was one tour from Berlin to Bangkok, which is close to 32,000 kilometers. So there was a Volkswagen car. They loaded these porous materials, and without refilling multiple times, they could drive the car. Okay, that was the thing. Okay, I'll not take them. And whatever our materials people have developed, they have already achieved 10% of hydrogen storage, which Department of Atomic and Department of US Energy Department, they have estimated for 2025 6.58%. So these materials are very efficient, already achieved the target, DOE target. But the problem is that these values are not at room temperature, ambient condition, so low temperature. Even bringing low temperature and all also energy loss. So people are trying to get a new, so new technology so that at room temperature can we maximize the storage. Okay. The other things like Government of India initiative, I have collected some figures. So 20,000 crore to 6,000 crore for production. Production linked incentive. The Government of India has announced 20,000 crore for green hydrogen mission. So our government is really thinking for getting this hydrogen technology more and more, so that our people and industry will be benefited. And so far as the cost is concerned, like 1 kg of hydrogen can drive you 100 kilometers or so, and it can also produce 16 kilowatt hour of electricity. And the cost, 2030 by US, they are targeting the cost of hydrogen per kg would be around $1, okay, which is roughly 100 rupees for us. But yeah, so there are several directions people are trying to bring this cost and integrate different technologies so that we can have better things. So we already know that Toyota Mirai car, they have launched in 2014. That can that is based on hydrogen technology. So 650 kilometers it can drive in a single charge, the fuel cell based technology. Several trains in Europe, they are driving using hydrogen as a fuel. Okay, that also a few things are coming up in India. Yeah, so China is also very actively doing research to get hydrogen technology so that their carbon burden and things will come right. So at the end, I would like to say that more planning, more like stronger policy, rigorous R&D, research and development is needed to come up with some interesting solution. Because the problem is for all of us. Unless we think now, how can we serve our kids in the future? So yeah, being experimentalist, actually this is the good thing what Dr. Amarendra has done. Like he chosen us that okay, scientists should be part of this thing so that we can give some input, whatever little knowledge we have, so that policymakers can make this thing. So it is a kind of joining hand things. We are in NISER, we are trying to establish some center or something so that we can do very vibrant energy research and also policy making so that we can contribute our part to the nation. So thank you very much.
Thank you so much, Dr. Prasad. So I was thinking that how do we transport all this green hydrogen at negative 250 degrees Celsius and 700 bar pressure, right?
Yeah.
So for that we need energy fiber, right?
Yes.
So we have to think and tell us how do we transport the green hydrogen at room temperature so that we can run our car or any other device. Okay. So thank you so much. Now we can open the floor for discussion. 5-7 minutes. We can take some questions.
I have a question to Dr.
Yes,
Sahu.
please.
Yeah, okay. The polluters pay principle. What about, you see, this carbon sink, the atmosphere becoming a carbon sink, this is a limited capacity. Otherwise, this ppm level is going on increasing and this thing. What about those people who has already polluted, already taken the space? Why don't you price them? Why don't you advocate to penalize them so that the developing countries who are really not very rich, poor countries, they can be benefited, number one. Number two, if you price the carbon now, who is going to pay ultimately? General public has to pay. You are increasing the cost of energy. You don't have a technology, low carbon technology sufficient enough to meet the energy demand. Everybody agrees with that. If you increase the cost further, then are you able to pay? The general public is able to pay. And that is not going to solve your carbon dioxide problem. Okay, you can generate some fund, but that problem is not getting solved because you don't have that much of technology, that much of resources to meet the demand. So is it this proper way to go?
Then nobody is listening if that's the problem. Nobody wants to take historical responsibility. That's the basic problem.
Yeah.
Exactly.
So,
Yeah, exactly.
So, okay, so to start with, it's a shared responsibility by all of us on the planet. Definitely, the developed countries have polluted, and the only way to argue with the developed countries, give us technology at a cheaper cost, which is not generation -1, but what generation you produce. For example, we always get one generation -1 here, right? If they produce 4G, we get 3G, and we install 2G. Just a case study.
Yeah.
So, one way is the cooperative mechanism for developed countries or low-income countries rather, because that word is out of the World Bank now, developed and underdeveloped. So low-income, medium-low-income countries have to join together, argue that we need technology. That is the only solution where we can reduce carbon. Financially, we cannot reduce carbon. That is absolutely, I agree on that. It is only accounting framework that we are talking about. But there is an advantage of financing mechanism. The advantage is it can generate carbon trade, it can generate carbon finance, it can generate circular economy. For example, if we talk in India today about solar PV generation, if we talk about renewable energy generation installations, then we need a recycling industry. So we don't have recycling industry very matured in India, which is a requirement today. Because the waste that is generated, right now we are talking only about flow. We are not talking about waste as a stock that has been accumulated and what to do with stock. And the recent news, if you look at, China stopped taking waste for a few months. That created a big problem because China has a monopoly on waste also. So that brings the idea of creating a new sector in India through these financial outlays. And the first question is, who is going to pay? Obviously, part of the burden will come to the consumer because I maximize my utility by consuming something. So I have to pay for it. So there has to be differentiated cost for differentiated products based on the emission profile.
That is what. Ultimately, the public has to pay.
No, public has to. My view is public will share the pay. It's not public has to pay because
Where from it will come the differential amount? Where from it will come?
Yes, so industry has to adopt technology, allow finance to reallocate in such a way that it can help increasing the technology spillover. But yes, the public has to pay because we are dependent on the utility that is derived by the industry. And the industry argument is they don't want to produce carbon dioxide. They want to basically come up with output. And there is a bad output generated in the process of production. So the idea is, unless we generate money from the consumers and the industry, create a carbon profile, come up with carbon trade mechanism, put it in the public finance activities of India, then we are not going to solve the problem.
This pricing the carbon, again you are going to pay to the developed countries. They have the low carbon technology, let's say, low carbon technology. And so they, you see, yesterday Mr. Puri was pointing out the same thing. for every policy or every advocacy, there is a hidden agenda behind it. So again, they are going to be benefited by selling the carbon certificates or whatever. They are going to. So the poor people pay again goes to the pocket of the rich people.
Isn't this true for any other product? How is it any different?
No, it's not true for.
Okay, for example, this one. This is a technology. The technology product I am using. The major chunk of the profit is going to Apple in this.
See, you have a choice to use this or not to use this, but you don't have a choice to energy. You have to.
Why
need
don't I have a
energy.
choice to use the energy?
Then go back to that old days.
No, I'm not saying that. Of course I have a choice to use the energy sources. Why don't I have?
Is it available? The alternate
That's a
source is
different issue.
available.
That's a
Is it-
different issue.
No, this is the issue. It
I'm
is not
asking how
available.
is it any different from any other product?
By pricing?
By making a person pay for another person's
No, paying.
alleged.
It has to be done. You pay for one product to me, and I pay for the other product to you.
There you are.
What the poor people are selling this
What is poor versus
you,
rich?
you don't say the total system work like that only, whatever you say. I'm just asking about the carbon pricing. By making the carbon pricing, are you going to help the environment? That is my question only.
I'm asking how this pricing is any different from pricing of a laptop?
I think
Okay, so- No. I mean, see, every product has an externality that comes. Some of them we know, some of them we are yet to know. For example, using this for 3 years and then just leaving it creates a waste, right?
It's a
So
question of dependency.
Yes.
It's a question of imposing dependency. That's what I'm looking at.
Suppose in the electricity you are using,
Mhm.
so it also emits some amount of CO2.
Everything emits.
No, electricity,
Every
no,
emission.
electricity you are using, it emits some amount of CO2, whether it generates from the renewable and non-renewable resources. Okay, and going by the thermodynamics rule and entropy putting there. But still, suppose you try to put that elasticity of demand and say that, okay, I'll put the peak event tax on this and because of externality and increase the prices. Who will pay for it?
You're back to square one now, fair.
no, see,
Who will pay for it?
Somebody
And the
has to
second
pay.
thing, whether government can increase the price?
Yeah, that's
It's
exactly what
impossible.
Santosh is
Government
saying.
cannot
Somebody
increase
has
the
to
price.
pay.
no, see.
Because it will be huge cry in the
See,
assembly and
the
the
way,
parliament.
see the way, no, that's a political thing, let's not go to
Entirely
that.
different
See,
debate.
for example, to buy a pen, I pay tax. Now this, for example, I go to a hotel, I pay GST and today I also pay a service charge. So that is not in my control, the market is anyway taking tax.
Okay, may I just,
Yeah.
I will give an example to see how the prices work and how price is such a powerful instrument in economics. A few days ago, when you all went to a shopping complex, particularly Civic Bazaar or any other shops, you were buying a lot of things, and the carry bag used to be free. So for every pair of dress, you wanted a carry bag, okay? Because you said, "No, I will be gifting it to my friend, and so give me 3-4 carry bags." When you introduce a price, and the seller is asking, "Sir, you want a carry bag? Smaller one is 5 rupees, bigger one is 10 rupees. You say, "No, I have brought my own carry bag." Right? So that's how the price works. Price really works. And when you are saying, okay, you may say that, okay, now for this technology, Americans have this technology, but our scientists are also working, right?
So that is true. Provided you have an alternative.
That's right.
Even
No,
the carry bag, you had an alternative
No,
to carry
that's
from
right.
your home.
Now see-
But here there is no
No,
alternative.
we have
It
actually.
creates
See,
such a narrative.
No, whether it's
Saying that West is imposing certain things on us is a very poor argument.
No, I don't agree with this.
No, it is.
Don't
It's
agree.
true. I'm not saying they're not creating.
Sir,
See, our alternatives are whether you want to choose NTPC or say nuclear or say solar or hydrogen or anything.
Can you survive as of now, or let's say 20 years down the line, can you survive? You means India, can you survive without coal? Tell me yes
See, it's
or
not
no.
either or. It is a mixture of everything. We may reduce the composition. I'm not saying that you can make zero, say NTPC. No,
You have seen
it will be
statistics.
everything will be there. We will have a mixture of everything.
No, that is true.
Yeah.
Okay, that mixture is going on.
Yes.
You have seen the statistics given by Dr. Nayak yesterday. You do not have that resources. You cannot. आप लाख कोशिश कर लीजिए, you cannot meet the energy demand through renewables. You have seen it.
No one is saying that. I don't think anyone is saying that.
So pricing
The question
carbon.
is about having a good energy mix.
Mix, that's what.
See,
That is
sir,
true.
Not
like-
complete replacement of
sir,
renewable
Exactly,
energy.
that's not possible.
Just
That's
one
definitely
minute,
not possible.
please. No, one half, 30 seconds. Sir, water is a free good, used to be a free good, right? Somebody priced water. And people laughed at that economy saying that he's a man who priced water.
Now you look.
Today you have, charcoal water sold at a larger price than anything else. So prices have given you alternatives. If you impose price, people would basically benefit by inventing new technology. But if we say that prices will not help us, then obviously we are standing there where we are standing.
No, no, I
And,
just given
sir,
argument.
give me half a minute, half a second. So in absence of a carbon price argument in India, we are going to accept whatever Europe is going to tell us, whatever
Exactly.
US is going to tell us. Do
Exactly.
we have a framework without, with understanding the energy profile and say this is our price? Then we have a market in international trade, we can fight with them. Otherwise what happens without any choice, we are going to depend on the European market pricing or Indian market pricing. So having nothing is definitely worse than having something on board to start the discussion.
No, let me ask you a simple question. Like, okay, so most of you are talking about renewable energy sources or other sources. Okay, so now everybody is talking about, okay, because now the price is much higher, renewable energy sources, that's why most of the people are not using it. Suppose when the production increases, given by the economies of scale, the price will come declining. Okay, when the price declines, it may be cheaper than the thermal power. Down the line, 30 years, 40 years,
Possible.
it may be cheaper than the thermal powers. Okay, so people, given it's a cheaper and having notion that okay, it may not contribute to greenhouse, may not environmental bad, people start using more amount of resources. Okay, going by the entropy law. Okay, going by the entropy law, putting the entropy law in picture. Okay, whether that is a sustainable solution.
Okay, see, everything that is being created is not infinitely sustainable, neither coal nor solar. Okay, we are going to develop something else. For example, people start talking about floating solar today. They were not talking in the initial periods. So we have developed in the technology front. That is where your price will come down. See, price will not come down only because of economics of scale in absence of technology. Unless there is technology, you cannot produce more. Right? So technology has to revolve and we have to accept that technology will revolve along with the price reform.
Okay, so I think we can go beyond our price. We can talk about other speakers. Yeah, I think Professor Grover has.
Here, let me say that Samuel's original question was that whether any efforts have been made with regard to holding the developed countries responsible for the historical carbon emissions. Answer is yes, but difficult to make them agree. They are the ones who are always ruling, but all the negotiations, if you see, I think this is what Ambassador Puri also started in the beginning, that the first conference, COP1, they started with common but differentiated responsibility. It don't matter. We are taking a decision, you follow it. It is an imposition by developed countries on the developing countries. The centrality of UNFCCC mechanism has been challenged by introduction of CPR. So this developed world will keep on coming up with instruments to subjugate the rest of the world. And the only way out is we have to develop. So we have to work harder and harder and develop ourselves. There is no other way to.
The council will never agree with the
Yes. So we have to do that, and this is all the history tells us all that what is going on. So now I think we move on to other thing. Maybe I can ask this question regarding. We talked about paint on the solar cells. Paint on the solar cells, and then with the help of it, efficiency comes out to be 25%. Now, this paint you said has life of about 2-3 years, while solar cells below will have a longer life. How do you manage these two different lives? I mean, one life duration for solar cells and paint. Is it that paint can be repainted on the same thing, or how will it go about?
How exactly we try to do it is so when the efficiency falls down to around 0.5% of where we started, then that's what we define in this case as the lifetime of the paint. So then we can wash the paint with common solvents, like it would be as water. So we can wash off the paint with the water, and then because there is a protection layer which protects it if you do not have. So once you remove the protection layer and remove the paint, then we can repaint it and put the protection layer again, and then we get back the efficiency. So this we can demonstrate.
Then secondly, you talk about supercapacitors as solutions for storage. Supercapacitors have their own limitation. I think in this connection you get in touch with the VRC, there is a group working on these capacitors. They have made capacitor banks for various purposes. In the beam technology group, Dr. Archana Sharma is the current group director. We remain in touch with him to know more about this subject. Okay, thank you.
No, how much electricity is required to electrolyze 1 kilo of hydrogen?
Exact numbers, no, actually it varies. So whether we are doing lab scale or like industrial scale or something, actually this technologies, whatever we are working on, basically, it's very premature. Like in lab scale, we get micromole, millimole hydrogen generation. Okay, but electrolyzer, it costs. I do not have the exact value, how much in that industrial level, how much it is, because we do in lab scale, so I do not have much idea.
Because ultimately the energy equation has to work.
Yes.
Because if my input energy is much more and I only reduce the carbon emission.
No, I don't think that is the case, because that is why we say that it's 70 to 80% efficient. Okay, and you just need electric input to drive the reaction. Once the reaction is driven, then you no need to supply continuously. It's very, sir? Maybe sir.
Well, I think the hydrogen which is currently being produced, it is being produced by reforming the natural gas. So that is why it's quite cost competitive, maybe $1. If we want to use electrolyzers for production of hydrogen, now here you are first converting electricity to hydrogen. There is some efficiency involved. I think claim varies from numbers vary. Then you convert again electricity, hydrogen to electricity in fuel cell, again some efficiency. So direct use of electricity wherever possible is superior to going via this electricity to hydrogen to electricity. And this efficiency can, total efficiency of the complete cycle can be as low as 50-60%. So, for example, in transport, my personal view is electrification of railway tracks is the best way forward. Directly use electricity and you can move passengers as well as goods on rail tracks. We are talking about hydrogen trains and all those, but supposing there are certain isolated routes where number of trains which pass through those routes, maybe one service in a day, maybe hydrogen powered train will work. Otherwise, electrification of tracks is a way forward, and same thing is applicable to buses and trucks. Electrification is better. In Europe, they have analyzed that hydrogen powered trucks versus battery driven trucks. In Europe, they have a regulation that the driver has to take rest every 4 hours. When the driver is taking rest, he can always charge the batteries and move on. Will hydrogen powered trucks work? Many people are skeptical about it, but still work is going on in that direction as well. On hydrogen, basically a lot more needs to be done, but what he was trying to say, if we can have in place of photovoltaic cell, we can have some kind of devices which conduct solar energy directly to hydrogen. That will be a total paradigm change. If that becomes successful, we do not know where we are going to be. So that is the way, if that research is able to give us results, in place of photovoltaic cells, we have photohydrogen cells. that we produce hydrogen directly, that is the second source of hydrogen can be this municipal urban waste and biomass. From there we produce hydrogen, that is another issue. But from using electricity to hydrogen and back to electricity, there I think one can have doubts. Exception to this will be aviation fuel. Storing hydrogen is going to be difficult. There one may have to convert hydrogen to something like dimethyl ether, ethanol, methanol, whatever works for aviation fuel, because there it will be used. So there are a lot of issues here, and one has to again analyze the system as a whole, not just what is the final system efficiency and move on that basis. Thank you.
Thank you so much. I think we'll conclude this session. And yeah, I think we'll conclude the session and then move to the